lot of students, when they first start taking physics, are concerned that they're going to have to memorize a ton of equations. There's a couple of things that make it better than that. The first is that any equations we have are going to describe real things that we can measure and observe. So we're going to collect data and try to fit equations to them. That's going to make it a lot more real and a lot more easy to picture why we have the equations. The second is, in this first unit, the equations we're going to be fitting are ones that you know really, really well. The slope-intercept form of a line, y equals mx plus b, and the slope formula, the change in y over the change in x. So the only tricky thing about these first equations is just understanding what the letters mean and what we're actually studying. So in math class, you've mostly used the x-y axis to plot your points and write your equations. So it literally corresponds to how far left and right have you gone? That's x, so I put in meters there. How far up and down have you gone? That's y, so I put in meters there. So this is the path that an object thrown through the air takes. And as you can see, it's definitely moving through space. And we can describe its location at any point with an x-coordinate, how far left or right is it, and a y-coordinate, how far up and down is it. Space is really 3 dimensions, so the z-axis would be coming straight towards you right now, and obviously it had a z-coordinate as well. In our class, though, we're going to really limit our studying to the 2 dimensions of left, right, and up, down. I don't know how much attention you paid to this statement, which I know you've written a lot in math class, but f of x means that y depends on x. That as I go this way, it causes a change in that way. In science, we'd say this is an independent variable, that's a dependent variable. That may not be true for physics. It may not be true for motion at all. In fact, we're going to see that motion this way and motion that way often don't have anything to do with each other. But what definitely does seem to matter, and what position does seem to depend on, is time. Where it is and how long it stays in that place really seems to change as time passes. And that's because this motion is not constant. And if we really want to understand what's going on with an object's motion, we have to collect not just distance data, but time data. So that's going to be the goal for the next couple weeks of the course. We have to constantly collect data about position and time. So instead of looking at y as a function of x, we're actually going to look at x, your back-forth position, as a function of time. So look at what that does to the graph. Time becomes one of the axes. And this would correspond to, say, 1 second, 2 seconds, 3 seconds. Now, because we made time one of the dimensions, we don't have room for both of them. So we actually would have to treat x and y separately. To keep things simple at first, we're going to look at objects that only move left or right, or x-axis motion, like, for example, these model trains. Or purely y-axis or vertical motion, like when I throw this angry bird up in the air. At first, at least, to keep it simple, we're really going to try to avoid situations where it moves both in the x and y dimensions. We'll just focus on one. So that's what we'll be on to next week. We'll be collecting data on when an object gets to a certain location. We'll be making a graph of time versus position. And we're going to stick it first with objects that move so that their time versus position graph is linear. And the advantage to that is that we can use the tools you've learned from graphing, the slope equation y equals mx plus b, to come up with an equation that describes that motion. So that's where we're going next.